integration of multiple open source components for image deconvolution. Hope you enjoy it. Yeah.
Okay, so just a quick question. How many people here have any kind of sort of engineering or image processing, signal processing background? And but you all have sort of a computer science background? Okay, well I'm going to try to really focus the talk more on the sort of the algorithm talk side of things and the open source side of things. And really, so if you see a few equations come across the screen and you don't understand it, don't worry about it too much. We'll really try to hit the concepts that are important for open source. So yeah, I'm Northan. I'm from True North Intelligent Algorithms, and the presentation I'm going to give today is on the integration of multiple open source components for image deconvolution. Okay, I've probably already confused the heck out of you with the title. For people without an image processing background, the important thing about this presentation is testing, algorithm testing and verification. Another important concept that is relevant to anybody in computer science is grand challenges. And of course, open source is important. That's what the conference is all about. And we'll actually, given the type of audience we have today, we'll sort of deconvolution will just be an interesting problem to try to illustrate some of the other concepts. So, quick outline of the presentation. I'm going to talk about the challenge that inspired this work. And I think the concept of a challenge is something that is probably important, should be important to all of you, because no matter what your interest is, you can find these challenges out there. There was just recently a public health challenge just before Christmas where they invited students from all over the place, and groups of students like yourselves all came. One group, I think they were just classmates or something, undergrads, they beat everybody, and they won like $6,000. So these challenges are really cool. You should always, you should keep an eye out for them. Then I'm going to talk about algorithms, like in a really, really general sense. Then I'll really keep it light on the deconvolution. This isn't really meant to be like I could turn this into a hardcore image processing presentation, but we'll try to keep it a little lighter. I'm also going to go over some open source tools. I'll keep that section brief. If your interest isn't primarily image processing, it might not be that useful for you, although they might be useful for anybody who does scientific computing. And then the last section is going to present some results. Now, even if you don't understand the algorithms, I think there's concepts that are really important here about how to get the right results and how to evaluate your results. So that's really the thing you want to keep an eye out for. Not so much understanding the technical algorithms, but just understanding how to approach problems so you can get the correct answer. So a little bit about me. I'm a systems design engineer. I've worked in image processing for over 10 years, done all kinds of different projects. So True North Intelligent Algorithms is just really a means for me to do contracting and consulting projects. And the niche I want to attack is sort of the little guy. There's lots of really good large open source projects out there, but I want to work with smaller algorithm developers and help them get their products to users. And I think a really good way to do that is to try to help them integrate with the big guy. So you guys have heard of Kitware. They're the company that, one of the companies that sponsored this course. And they make a big open source library, several big open source libraries that's used by everybody. If you're a little guy and you can integrate your stuff with theirs, all of a sudden it's accessible to all kinds of people. There's another thing called Image which I'm going to talk about. It's the same idea. It's very big. If you're somebody little and you can get your work compatible with Image it's available to all kinds of people. So let's talk about the challenge. So what's a challenge? I explained it a little bit. It's just sort of a contest. And when I was your age, I never even heard of a challenge. I never even knew they existed. But it seems to be a really popular way of sort of getting people involved with different types of technology. And again, keep an eye out for these. Like whatever your niche is, you can probably find one. You might even be able to win a little bit of money or make yourself known, get a job. So for the last few months, I've been involved in something called the Second International Grand Challenge on 3D deconvolution microscopy. And this is sort of a niche challenge. You find these things by going to Google, trying to find out discover things about groups that are interested in the same things you are. And these things are open to anybody, so anybody can participate in these kind of contests. So the way this challenge was structured was actually really interesting. It really forced us to be open, and I'll try to tie that in later in the project. But first, I'm going to talk about algorithms. So what is an algorithm? Well, Wikipedia calls it a step-by-step procedure for calculations. How stuff works, well-defined instructions. And they give this sort of silly example, the get home from the airport algorithm. But I think it's actually a really, really good example, because it's, again, I'm sure that we all have our niches, and it's often hard to convey your niche interests, explain all the details of them to sort of a larger general group. I'm sure a lot of you, if you tried to explain some of your projects, I wouldn't be able to understand them in 20 minutes. It would take me probably days to start to understand them. But the get home, this example they give, the get home from airport algorithm, is actually just really, it's really general, so anybody can understand it. So one of the specific get home from airport algorithms is the taxi algorithm. Go to a taxi stand, get in a taxi, give the driver your address. This is important. Algorithms kind of have this resolution to them. So the high-level description of an algorithm doesn't always tell you exactly how it's going to behave. So this is really easy to understand with the taxi algorithm. There's every step has sub-steps and details. You go to a taxi stand, you have to walk through a terminal, take a shuttle, get in the taxi, you have to put your luggage in the trunk, sit down in the seat. And it's really important how the steps are actually implemented. So take the taxi algorithm. What if the taxi driver takes the long way, so he runs up the meter? Or what if he's a bad driver and he crashes the car? Again, it's kind of a silly example, but the steps are really important. And when we're dealing with algorithms, we also have this concept of open versus closed source. So again, take the taxi algorithm. I don't even know how you make a closed source taxi algorithm. I mean, maybe you get knocked out, somebody hits you over the head with a baseball bat, and then you wake up at home and you don't know how you got there. I mean, that would be kind of a weird experience. So I think, at least with the taxi algorithm, open source is definitely better. So I gave that sort of simple example so just to show some sort of these important high-level concepts. Now I'm going to try to relate it to a very specific lower-level algorithm. And that's called deconvolution. So what's deconvolution? It's a procedure used to reverse convolution. And all convolution is signal blur. Does anybody here ever hear of the Hubble Space Telescope? I think it was launched about 20-25 years ago. And when it went up, there was some problem with the mirror. And they started taking these images, it's this huge endeavor, and all of a sudden all the images are fuzzy. So they actually had to use computer programs to try to clear up the image. That's probably the most well-known example of convolution. Another one you sometimes see is on crime shows. They take a picture of a license plate with the car zipping away, and the license plate becomes blurry, and they use some fancy software, and all of a sudden you see the numbers and you catch the guy. That's another example of convolution is the process of the image becoming fuzzy, and deconvolution is the computer program that clears it up. And this sort of shows the concept. This is an image of a cell. When you take the picture, it's fuzzy, and you use your computer program to clear it up. And this slide here is just basically the same concept. You're interested in an object, but when you take a picture of it, it's fuzzy. And there's some other complications, because when you take a picture of something, it's of limited size. you can't get a picture of the whole universe. So it's usually a good idea when you take a picture, if you're going to do some sort of processing on it, to have a lot of space around the object that you're interested in. That's not always possible, so sometimes you have these, what image processing engineers call edge effects, where you have these sort of problems near the boundaries. And don't worry about this slide. It shows some of the deconvolution equations. This slide, again, is sort of going over, this is Richardson-Lucy is a specific approach to deconvolution, sort of beyond the scope of this presentation to explain exactly how it works. But the basic idea is if you take, have you guys all taken calculus? So you've dealt with, sometimes in algebra, you can solve equations directly, But in calculus, you've probably done optimization, where you have to take derivatives, and you have to solve the calculation. The derivative sort of gives you the direction of change of the equation, and you have these sort of optimization procedures where certain classes of equations, you can't solve them directly. So that's one of the reasons you need calculus, because you can frame the equation in such a way that you can sort of solve it step by step. It's like climbing up a hill. And that's what they do in deconvolution. One of the commonly used methods is called Richardson-Lucy. And a key point about this is that it's not really the best algorithm out there, but you get into these, there's all these other methods that have really fancy names, really complicated mathematical approaches, but the problem is they're not always open. So you can't double check, you can't modify it, and so the really nice thing about this method called Richardson-Lucy is that many groups have implemented it. So you can get your hands on not only one copy, but you can get your hands on multiple copies, and you can double check them, triple check them, quadruple check them. And that's, no matter what you're doing, that's really important. So in the open source world, when you're trying to get a piece of code, if you've done any open source, you've probably already experienced this. Sometimes the first time you search for something, Stack Overflow tells you where you can get something, you download it, and it might not work. So it's always great to have multiple implementations so you can debug them against each other. So the next section goes through some of the tools that we use for this project. Now, I had to use about 6 different code bases for this project. So again, your specific interest might not be image processing, but for any project you do open source, it's always a good idea to to combine sort of elements from multiple different projects. That's one of the really powerful things about open source. So I use this, one of the main things I used is this thing called ImageJ2. So if you ever do any image processing, ImageJ is a really, really cool tool. It's basically an application. It was developed by the NIH. It's free to anybody who wants it. The source code is completely open. And the cool thing is that it's extendable, which means you can write your own modules, and if you write them in the proper way, they'll automatically be open. They'll automatically be added to ImageJ. So, since you guys are mostly computer science majors, I think this will be maybe one of the most important points in the presentation for you. ImageJ is what we call a command-based architecture. So a lot of open architectures use that sort of same software pattern. So they might call it by slightly different names. It might be add-on architecture or plug-in architecture, but it basically tells the programmer how to program in such a way that the master program will pick up their module. And that's the most powerful thing about ImageJ. So this little piece of code that I'm showing right now, it's what's called the command ImageJ. And it's a really kind of simple command. It just makes an image, sort of a blank image with just a constant background. But the really cool thing is that ImageJ will recognize this. It'll automatically add it to the menu. It'll automatically generate a GUI. It'll automatically display any outputs that you have. It'll automatically keep track of input parameters. And this little piece of code is really powerful because you get all this. This GUI you see here, the ImageJ program knew how to make that just based on small little annotations that were in the code. So this whole idea of add-ons and plugins or commands, they're called slightly different things in different projects, but in anything you're doing, it's just a really, really useful concept. So if you ever have a project to do, you might not be, you don't have to like reinvent the wheel. You just do your own little part and write it in such a way that it gets like added to the car. And you know, this is another sort of screenshot of ImageJ. Another one of the really cool things is that when you write things, when you write your software in this modular fashion, the program can sort of keep track of what's going on. So what you're seeing here is sort of an image processing routine, but it's like a longer image processing routine with a lot of steps. And instead of just getting an output at the end, you get an output of each step, which is a really useful thing to have. Another library I used was something called ImageLib2, sort of a general process, a general purpose Java library, really useful if you're into any image processing. I also used something called Cosmos, which is really a niche library for deconvolution. Along the same line was a library called IOCBIOS. And I also used ITK, that's image processing, another powerful C++ image processing toolkit. The good thing about ITK is that it automatically generates wrappers for other languages. So if when you're looking for tools, it's really good to look for tools that are callable by multiple languages. So ITK, even though it's a C++ library, they've written it in such a way that you can call it from Java and Python and Ruby. Then you can, another thing I used, I'll just mention this briefly, is Octave. Have you guys heard of Matlab? So Matlab is a very expensive scientific processing program, and it's like really, really integrated into science. So even people who think they're being open, if they're using Matlab, they're not quite 100% open, because in order to be compatible with them, you have to buy this hugely expensive license. So Octave is like an effort for an open source version of Matlab. And it's a really useful project. Like if you need to look at some Matlab code and just sort of run it just to verify it, or just to test somebody else's results, it's really useful to be able to use Octave, so you don't have to buy the Matlab license. And this diagram here just shows, you know, sort of the concept of integrating different code bases. So you have these big projects like ImageJ2 and ImageLib, and the Cosmos project and the IOCBIOS project, those are really niche things. So, but if you can integrate them into something bigger, then you make those things accessible to many more users. So the final section is just going to go over some results. And I think the most important thing to gain from this section is just the idea of how to go about testing. So what I've done here is I've run some simulations. Anytime you are working on a scientific problem, if you know anything about the process that generated sort of the phenomena that you're trying to investigate, it's a really good idea to write a computer program to recreate sort of what we call the forward model of the problem. So make a simulation of the problem where you know what the original answer was, then try to solve that. And before you attack real life problems, make sure that your program gives you the correct answer for sort of these little toy problems that you ran inside the computer. So I'm going to show you some results, and what they show is this algorithm called Richardson-Lucy with 3 types of boundary strategies. Now, exactly what Richardson-Lucy is isn't important. Exactly what boundary strategies are isn't important. I think the important concept is that when you run an algorithm, the details really matter. Because in science, people even though they should, I think they should be very descriptive of what they're doing, they often use these very high-level names to explain what they've done. So people will say, I did the Richardson-Lucy. And if you're sort of an outsider, you guys don't know what Richardson-Lucy is. So if someone walked up to you and said, oh, I did that, you wouldn't know for sure exactly what they did. So if 3 people all told you they did Richardson-Lucy, you'd assume that all 3 were doing the same thing. But with any complicated algorithm, sort of the details of how you went about implementing it are like really, really important. So that's where sort of the open source comes in, that it's almost impossible to tell exactly what's going on without the source. So what I did is I ran this simulation. It was just a test object. It was 2 spheres in space. So you run your program. The program sort of simulates what happens in the microscope. It makes the spheres fuzzy. Then you run your deconvolution. And one of the problems, remember I mentioned this thing called boundary conditions. Well, all that really means is that when you take an image, you don't take a picture of everything in existence. So you don't know what's outside the image window. And it's sort of important how you assign those values. So I performed this deconvolution experiment using 3 types of boundary conditions. One called 0, one called Newman, and one called non-circular. And then I measured how bright the spheres were. So this simulation was dead simple. The background was 0, the spheres were supposed to be 100. So the answer is 100. And again, it's always just a really great idea to try to design like really simple experiments where you know exactly what the answer should be, and if it's off, you can tell what it is. So when I made the images blurry, the spheres only had a brightness of 4. So you can see how the blur process really distorts the image. Then I tried to get the value back. So what I wanted to do is I knew my answer, it's 100. I wanted to get 100 back. So one method got 74 for one sphere, 49 for the other. The next method got 88 for one sphere, 65 for the other. And the final method got 100 for both of them. So these are the types of experiments you have to, I know it sounds simple, but this is actually, this contest that was run, it was very, very difficult to sort of get the correct answer back. The problem, the fact that you don't know, remember I showed this image here, where you don't know what's outside of the image, sort of the kind of programs you have to use to simulate what's going on outside there are actually, I'd say, deceptively sophisticated. So the contest was set up so that you thought it was easy, but you really had to look into things to get the right answer. So that shows the value of challenges. Again, the details of this challenge, I admit, they're probably hard to appreciate unless you're really into image processing. But these challenges are usually organized by groups with sort of a purpose in mind. They set up the problem, they know something about the problem that you might not, and they set up the problem so that you're going to learn something. And the other cool thing about this is that the algorithm that works, that solves the problem correctly, was actually produced by the group that organized the challenge. And this makes sense, because I think they wanted to show everybody how great their method was. And they actually, on their website, they described the method in equations, and they also gave code to show how their method works. Now, it wasn't a simple method. It wasn't like you could just take their code and just run it. It was the kind of thing where it was just one little aspect of the problem, but you had to integrate their solution for part of the problem into your own solution for the whole problem. So it was a project that was just impossible to do without open source, because you needed open source to understand what they were doing, and you really needed your own code. You either needed to have your own code to solve the system, or you needed to use open source code, so you could sort of mutate it to follow their procedure. So the presentation I just gave is just sort of the tip of the iceberg for this particular problem. There's all kinds of things. They have, the experiment I showed was just one very small aspect. There's things called aberrations. There's noise problems. There's variant blur models. I'm sure it all sounds a little bit funny to people who aren't in the field, but any problem is like that. These are there's like 10 different factors to solve, and that's why open source is just such a great approach. No group has all the answers. So when what I did here essentially is I took several different code bases and solved the problem by combining them, and that's in the future I think that's the way all problems need to be solved. Just taking advantage of people who've solved part of the problem, and combining their approaches. Yeah, that's pretty much the presentation. Any questions at all?
How hard was it for you to integrate all like the add-ons and have them like talking to each other efficiently and actually get them to all be working in unison? Because I'm used to like working with web services, and you like send out a call. You have in like one web project you might have like upwards of like 10 different web services all being called from random parts, and it's really hard to like integrate all those together with like compatibility and stuff. So what's like the hardest part that you went through with all your add-ons?
I think the hardest part was learning to, so some of the code was in Java and some was in C++, and there's like a procedure to make sort of a wrapper around C++ code so you can reach it from Java, but it's very easy to make mistakes. So if you sort of run these utilities and they generate the wrappers, but the wrappers have these really long, strange names and everything. And as you make the calls, you have to be very careful in your that you're typing in everything correctly. Because just the way like if you're inputting two numbers, it'll sort of append n to the end of the function call name. It'll make these really complicated things. So it's just the accounting, I guess, was the hardest part. And the first time I did it, it probably took a few days to do it. It was really slow. But as I got used to the procedure, it was much, much quicker. So there's a little bit of a learning curve too. Go ahead.
I'm sorry, I stepped out, so you may have already spoken about this, but in the brief on this discussion, you mentioned ImageLib 2?
Yeah.
And so you're using that, and how is C involved in your project? Because it's Java.
Yeah, so C is, I use Java as much as humanly possible.
Yeah.
So I try not to, anything that's simple enough to, even if it's going to take me a week to rewrite in Java,
Yeah.
I rewrite it in Java.
Okay.
If it's going to take me months or it's way beyond
Yeah.
my capabilities, I write that was a similar question
Right.
to what the gentleman asked.
And
I use sort of this JNI utility to
Right.
write wrappers to it.
Right. And you didn't use ImageJ?
Oh, yeah. I
You
use
did,
ImageJ.
okay. So
I actually used, go ahead.
was ImageJ the front end? essentially?
Yeah.
And then you were using ImageJ 2?
ImageJ2 was the
Right,
front end,
oh,
yeah.
congrats. I was involved in the start of that project. I was on that project for 2 years ago.
Oh, you really?
Yeah.
Okay.
Yeah, we should talk more about specifics.
Okay, that's interesting.
Yeah. And I don't know if you talked about the history of that at all. I don't know if anybody would be interested, because in terms of the open source development on this,
Yeah.
ImageJ was developed at the NIH. This guy, William Raskin, is working on this guy. He's retired now. He's still working on it. It was kind of his life.
He answers every single question.
And he's
I know.
incredible, yeah.
Yeah.
And he's a big part of it, because when anybody asks a question with an answer, you change the code. But one guy basically wrote this thing.
Yeah.
But it was really 2D to begin with, and then it sort of got stretched to 3D, and then to 4D, and then to 5D as things got more complicated. And it became less and less sort of workable. It couldn't extend. It was designed in such a way that it couldn't really be expanded. And I was involved in a project that was funded out of, NIH funded it actually, one of the stimulus grants through Wisconsin. And there was a project still ongoing to build its successor called ImageJ2, which is a much more modular and well thought out thing. But and when we started that project, we then ran into the folks at Dresden, at the Max Planck Institute in Dresden, who built ImageLib 2. They were real computer scientists, and they built an all Java n-dimensional sort of matrix space for doing image processing in n dimensions. Everything's arbitrary. It's a really fantastic piece of work. And if you're looking for that kind of stuff, I highly recommend it. Then Image also spawned a couple of other communities. One is out of Dundee in England, or there in England or Scotland, and which is a database backend. It's a high-end database with metadata and all this stuff, kind of deals with the storage. And then at UCSF, another project sort of leveraged Image built instrument control and microscope control stuff. It's called Micromanager. It's out of UCSF. And so there's this really big community that has evolved from this one. It's not even open source, it's public. I mean, there's no license on it at all. Wayne is a funny guy. So, but that's kind of just the history of that and how it evolved. I'm glad to hear you're actually using it. Very few people actually started to use Image 2 yet.
Yeah, and I think that's going to explode in the next couple of years.
I hope so. Yeah.
It's
yeah.
There's a whole history behind that.
Yeah. Anyway, just
great. But it's this thing is, it's incredible how these things. Remember I talked about how the big guy, there's the big guys and the little guys, and if you can get your stuff, even if you're a little guy, if you can make it compatible with big guys, then you have it. You've made it so accessible because you walk into a room with people of all different backgrounds, and you know all about all this stuff, right? So whatever field you're in, if you can try to learn something about the big guys, and even if you're a little guy, if you can make your stuff talk to the big guys, you're always going to, you're going to make it so accessible for people.
And if I could add, one of the things that made Image so successful was its plugins. Early on, he understood that he needed to let other people write and plug it into the rest of the system, and those evolved and evolved to such complexity. That was really one of the real reasons for its rewrite and re-architecting, is that the plugins were just all different. There was no rhyme or reason to it, but nonetheless, all of those plugins allowed people to jump on the bandwagon, jump onto this infrastructure of Image, and so it's a great place, particularly in optical microscopy, to other imaging platforms. So building plugins into somebody else's existing open source framework is a great way to get sort of small pieces out into the world for people to use.
Hi. So I'm a maintainer of ITK, actually. And one thing that gives us a huge amount of headaches often is to continually support wrapping for so many different languages. But it's great to see that there's actual payoff to people who don't necessarily have completely native C++ application and they want to integrate ITK algorithms into it. And something we don't really talk about too much in open source is the fact that you have so many heterogeneous languages that often you have these niche tools that are most appropriate to the task, and they're written in a completely different and compatible language, and there's different data structures and different sort of execution styles. Do you have any advice on when it's really worth it to write the wrapping and to write the compatibility layers to other libraries, and when it's worth it to say, I'm going to focus on my own code, make the quality is high enough, and if it's great, people will come and do it on my terms?
That's a really interesting question. I think it would be really individualized. You'd have to sort of know your audience. Like one thing that I love about ITK is that, so I'm doing this really niche thing, deconvolution, and somebody from, I don't think they were associated with Kitware at the time, they wrote a deconvolution library in ITK out of the University of North Carolina. And I don't think anybody wrote a wrapper for that. I think it was automatically generated. But I sat down on Monday because I needed to double check results for this project, and I integrated ITK into it in about 2 hours. So I mean, it's just so powerful to have. You can't really anticipate, I guess, what everybody will need. So but to have it there, instantly, rather than have to write the wrapper myself or call somebody, was just an amazing experience. Now, on the other hand, to be efficient for the entire community, you might be better off just reacting to people, You might not be able to get it, it might not be like you get the wrapper the day of, but if there's all of a sudden demand, it might take you a little while to get it out there, but that might be better than, to be honest, I don't know. For me personally, wrapping everything is amazing, but for you, I'm not sure.
Could I comment on that? In working with this Image 2 project, one of the guys involved, actually, in the course of a day or so, wrote an interface to ITK. And I think that the reason he could is that ITK, I think, it's quite evolved and pretty well structured, so that your interfaces are exposed. Your API, the right things are exposed through the interface. You've got interfaces, and they're actually defined, and that really facilitates somebody coming in, whether from another language, particularly from another language, but, you know, unless you go right into the source code, you know, and actually, go in there, manipulate and break rules, you know, to get it done. Unless the API exposes, you know, if the API really exposes the functionality to sort of talk to, but that takes time to sort of understand how your thing might get used and what you can expose or not. But designing the interfaces is kind of the mantra of exposing stuff, in my experience.
I mean, maybe you just make a tool to do it if that's possible, because I know for me, the tough part would have been to wrap like ITK images, like if it hadn't been done, and I figure out how to go from Java to ITK. Like I can go to Java to C++, no problem with the interface of just like flow pointers and stuff. But to go, I might have had to, fool around with it and struggle with it a bit to try to get ITK images back and forth, stuff like that. So that maybe if you have like a tool that is specific to ITK Java wrappers, and then people can wrap I don't know.
Yeah, I guess I was just commenting on the fact that it's an interesting problem, because you always take the language when you're starting a project as whatever your favorite pet language is, or maybe what's most appropriate to your particular application. And then if you don't start with wrapping in mind, and you depend heavily on the idiosyncrasies of a particular language, later on when your library takes off, or your project takes off, and you want to integrate it, now it's too late. I have to go back and write all this wrapping, write all this integration again from the ground up. So it's, it's initial investment versus, payoff later.
Were you involved with simple ITK?
So I'm not directly really involved with simple ITK. That's a guy named Brad Ocamp who supports that. He's also an ITK developer, maintainer as well. So, and we work back and forth, but they're very closely working.